So we are continuing from yesterday. Yesterday we have found the expressions, operator expressions for L square and LZ. Okay. Have you done the homework? Minus h cross square 1 by sine theta dou by dou theta of sine theta dou by dou theta plus 1 by sine square theta dou square by dou phi square. This is the expression for L square, and expression for LZ is minus IH cross dou by dou phi. So yesterday there was an error when I didn't put a minus I, but I corrected in the notes that minus. Okay, you can check that. Okay, these two are the operator expressions for L square and LZ in terms of spherical polar coordinates. Okay. Now, I think you have tried this finding L square in the second method. That you should try, because you should familiar with some operations, simplifications of this algebra. So these are the two operators, L square and LZ. Now we have generally written the eigen state as ket LM. Okay, where lambda or L into L plus 1 is the eigenvalue of L square. So small l represents the eigenvalue of L square, and the m represents eigenvalue of LZ. So this is the general state eigenket of common eigenket of L square and LZ. Now we are going to represent the same thing, but in a different way. We are going to assume that the solution, instead of this one, we can write it as capital Y. Okay, which is the indices are YLM, same indices YLM, and the solution is a function of theta and phi only, no R term. So you can write YLM theta phi. Okay. So instead of ket LM, we are using another representation, another form, YLM theta phi. So capital Y is the solution or the eigen function of common eigen function of L square and LZ. So YLM theta phi. You might have studied somewhere what is YLM theta phi. Maybe in BSc also you think you have studied in solving the hydrogen atom problem. There the wave function. I think you may remember this psi of R theta phi. You written as separation of variables, capital R of R, then into theta of theta into phi of small phi. So these two things together you can call it as YLM theta phi. Okay, so these theta and phi components, part of the wave functions, together we can call it as YLM theta phi, and it has a special name which I will tell later. Okay, so YLM theta phi, that is usually known as spherical harmonics, which I will explain later. Spherical harmonics. So according to our idea of eigenvalue equation, what is L square? When L square operator acting on YLM theta phi, result is lambda YLM theta phi. But what is lambda? L into L plus 1 H cross square. That is the eigenvalue of L square. This is already we know from the earlier sections. We know eigenvalue of L square is lambda H cross square, or L into L plus 1 H cross square, then YLM theta phi. Okay, so this is the eigenvalue equation because YLM theta phi both are same. L square is the operator. So operator acting on a state eigenfunction, you get eigenvalue into eigenfunction. So this is an eigenvalue equation of L square. Similarly, eigenvalue equation of LZ, that is similar because YLM theta phi is a common eigenstate. So YLM theta phi, LZ acting on YLM theta phi, we get eigenvalue of LZ is M H cross M H cross YLM theta phi. These are the two eigenvalue equations of S square and LZ in the new notation. Instead of LM, we are using YLM theta. Okay. Now let us first find some of the properties of this YLM and find the exact expression for YLM theta. So take the second question. We know what is Elizabeth. Elizabeth is substitute for Elizabeth minus H cross dou by dou by. That is Elizabeth. Okay. This we found in the last class. So that is acting on YLM theta phi equal to MH cross YLM theta phi. Okay. So the H cross is on both the sides, they cancel. H cross cancels. Then you just simplify this and integrate. So that is minus I. Let this minus I go to the other side. Then what remains here is dou YLM theta phi divided by YLM theta phi equal to IM. You multiply with a minus I on both sides, I on both sides. So here it becomes plus 1 and here it becomes IM. So IM into dou phi. Separation of variables. YLM dou y by y equal to IM dou phi. Now you integrate. You get log y here. Then you cancel that logarithm with exponential. Then you get YLM theta phi equal to e to the power of IM. This integral dou phi is phi. This we have did many times, so I am simply writing this. So in addition to this, there will be a constant. Here this is proportional to, so a constant will be there. So you can write take logarithm along with that constant, so you can add, you can multiply with this. So put that constant as f, flm, which is a function of theta only. Phi is already here. Now what remains is theta. Here is theta and phi is there. So e to the power of im phi is a function of phi. So this constant will be a function of theta. Okay, because we are operating with the dou by dou phi. Only phi is the variable, theta is the constant. So put that constant as f lm theta into e to the power of im phi. Okay, I think that is clear. So this is the normalization factor, normalization constant, flm theta. Now we have some fundamental properties of wave functions, so you can apply that property for ylm. One is ylm should be single valued function of theta and phi. Many properties are there, continuous, derivative, continuous, like that. But one property is ylm should be single valued function of theta and phi. Okay, now let us apply that property. Ylm is a single valued okay. So we are going to apply that single valuedness of ylm theta phi. Okay, ylm theta phi should be single valued of theta and phi. Okay, so that is one of the boundary conditions. So you can write that that is ylm theta. So when phi you increase the by 2 pi radian. Okay, so theta remains same, phi you change it by 5 plus 2 pi, then it should be same as ylm theta phi. This is single valuedness. So means 360-degree rotation, the solution is same. That is the meaning. Okay, so ylm should be same after 360-degree rotation, because this is orbital motion, circular motion. So you apply this condition in this equation for ylm theta phi. So ylm theta phi equal to flm theta. Ylm theta phi equal to flm theta, then e to the power of m is a constant, then 5 plus 2 pi. That should be equal to flm theta e to the power of im phi. That is the meaning of that one, single valuedness. E to the power of im 5 plus 2 pi is e to the power of im phi. For this to be true, what is the condition? This is true only when e to the power of im 2 pi is 1. So this is true only when e to the power of im 2 pi from here, that should be 1. this should be equal to 1. Okay. So from this, what is the allowed values of m? That is the question. So m can take values. This e to the power of im 2 pi is the cos theta plus I sin theta, like that. Cos 2m pi plus sin 2m pi. So m can take values. M can take values 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. M can take values, integer values, plus and minus. Okay. Now we have already know that what is L? L value is the largest value of M. From the discussion from the eigenvalues case, we know L is the largest value of M, or M is the component of L, or the reverse is L is the largest value of M. Okay, so L can be a positive integer or 0, because M values are 0 and plus or minus these things. The largest value of M is L. So we can assume that L is positive or 0, not negative. Negative values are lower values. So maximum value is the positive values. Okay. So L value is positive integer or 0. So we can take what is L? L as 0, plus 1, plus 2, etc. up to any higher value. And the M values are minus L plus 1, minus L plus 2, etc. Last value is plus L, and just previous value is L minus 1, like that. So the same ideas what we studied earlier. So there are 2L plus 1 values for M. All this idea we obtain here also. By studying this solution for LZ, we get the concept of eigenvalues small l and small m and their ranges, their values. Okay, all ideas which we studied earlier we get from here also. So this is we have considered only the integer orbital angular momentum, so only the integer values will come. We have considered only the orbital angular momentum, so only integer values are allowed. So orbital, since we have considered orbital angular momentum, L can have integer values only. When spin comes, half integer comes. So, but we have studied only here the integer orbital angular momentum. So only the integer values of L will come. Now also we don't know what is YLM theta phi. These are only some of the properties of YLM theta phi. Now to exactly find the YLM theta phi, we have to consider the operation with L square. Okay, so L square acting on YLM theta phi, result is lambda h cross square, or L into L plus 1, that is lambda, H cross square, YLM theta phi. Okay. So YLM theta phi, what are the properties of YLM theta phi? YLM theta phi is a normalized eigenstate. Normalized, should be normalized. It should be the common eigenstate of both L square and LZ. Okay. And we have seen that this L square we actually obtained from the expression of del square. Del square actually contains this L square. Okay. So del square operator we usually call it as Laplacian operator. So that equations, Laplace equations, if you write with the del square, it is Laplacian equation. So solutions of Laplacian equations are known as solutions of Laplacian equations are known as, what is the name? Name is harmonic functions. Harmonic functions. Solution of Laplacian equations are known as harmonic functions. Now, actually, this is L square. We know only the theta and phi contains. It is actually YLM theta phi is the solution along the surface of a sphere with a unit radius. So YLM is the solution on a sphere with a unit radius. Therefore, we call YLM as YLM theta phi. Normally, solution is called harmonic function, but this is why our YLM theta phi is the solution harmonic functions on a unit sphere with unit radius. So that YLM theta phi we call it as spherical harmonics. So that is an important name, spherical harmonics. YLM theta phi is known as spherical harmonics. What is spherical harmonics? Solution of Laplacian, solution of Laplace equation on a sphere with a unit radius. So that is why the name Laplacian, spherical harmonics. Okay. Now we are going to find the exact form of YLM theta phi. So you have to solve this equation. Solve this equation, that is the only option. How to solve this equation? This equation you can write it as L square YLM theta phi, okay, then minus L into L plus 1 H cross square YLM theta phi equal to 0. Okay. Now how to solve this equation? That is the question. So this is, you have to do a lot of substitutions for many things. L square, okay, you can substitute for L square. So what it becomes, what is L square? L square I have written today. Where is that? We have found in the last class. This is L square. So substitute for L square here. That is the first step. Okay, substitute for L square here. So L square is this one, minus h cross square 1 by sin theta dou by dou theta sin theta dou by dou theta plus 1 by sin square theta dou square by dou phi square. Okay, so let me do that. Okay, let me do that. Now the next part is not easy, but we will try. So L square is minus h cross square 1 by sin theta dou by dou theta of sin theta dou by dou theta plus 1 by sin square theta dou square by dou phi square. This is L square. Okay, so L square into YLM theta phi. Okay, L square into YLM theta phi minus L into L plus 1 h cross square YLM theta phi equal to 0. So our differential equation becomes like this. Now if you do some substitutions, put u equal to cos theta, put u equal to cos theta, then this equation becomes, I am not doing that, 1 minus u square d square by du square minus 2u d by du plus L into L plus 1 minus m square by 1 minus u square all into, okay, w of lm u equal to 0. So this is not easy,